constituent element is the O2, not just O. As same as with the hydrogen, it appears as the H2, not N2. Right? So the first thing is you have five species here. You want to determine how many independent chemical reactions. The first step that you have to do is writing the formation reaction for every compound in the system. In this one, you have 4 compounds. 1, 2, 3, and 4, not counting the hydrogen. Not counting the hydrogen gas. The hydrogen gas is considered as the element in this case. So that means that you have to write for formation reaction for the carbon monoxide, hydrogen, and methane group. And for carbon monoxide, it comes from the carbon atom plus with the half mole of oxygen. Then you get the carbon monoxide. Or the methane, the number 4 here, is comes from the carbon atom plus with 2 mole of hydrogen gas. Then you get the methane. It's just like that. Or water is comes from the gas, hydrogen gas, react with half mole of oxygen. Then you get water. Then the second step, you just pick one equation and combine with the remaining equation to eliminate the particular element that is not present in the system. The element that is not present in the system in this case is the carbon solid carbon here, and the oxygen as well. Yeah. Solid carbon and oxygen actually is not present in this system. You have only hydrogen, carbon monoxide, water, carbon dioxide, and methane. So in this case, I want to eliminate carbon and oxygen. What it is starting from eliminate carbon atom first. So I use the equation number 2 here minus with the equation number 1. So in final you get the number 5 here, which is you set with 2 minus with 1. So the carbon is eliminated, and the oxygen here is the main half mole here, and the carbon monoxide is here, and carbon dioxide is here. So the meaning of minus is just flip the reaction. We have number 2. And this minus number 1, right? Minus number 1 is the CO, and C plus half mole of oxygen. It is correct. Here. So C is here. You have this, and you have half more of this, and oxygen is eliminated. Then you get the reaction number 5. You did the same for the second one. You fix the equation number 2 again and minus with the reaction number 4. Then you get the reaction number 6. So another step is it actually in the same step. First eliminate the carbon element. Now eliminate the oxygen molecule. So this is the set from the previous slide. Now we have the remaining equation of number 3, 5, and 6. Number 1 and 4 have already used. Number 1, 2, and 4 have already used. So the remaining equations here is number 3, 5, and 6. So from number 3, 5, and 6, I continue to eliminate the oxygen molecule by breaking the equation number 3 minus the equation number 5. Then you get the equation number 7. Again, I use the number 6 minus with the number 3. Then you get the equation 8. So right now you have already used all of these 3 equations. And now the remaining equation that you get in the final is number 7 and 8. So in the final it means that from the system that you have 5 species of the carbon monoxide, water, methane, and hydrogen, the possible number of chemical reactions that can occur in the system is 2 equations. This is the set of independent reactions. So if you calculate the degrees of freedom, you have the number 2 here, which is come from the equation number 7 and 8. You get the 4 degree of freedom. It means that the system is very complicated. You have to fix 4 parameters, then you can fix the system. Okay, so the point here is I want to make sure that you know the step of determining the number of chemical reactions. Step 2, determining the independent reaction here, which is needed when you don't know the actual chemical reaction, but you just know the species that exist in the system. You will see the example. Okay, so from here, okay, just a little bit to slide and then we can have a break. For the multi-reaction system or multiple reaction, how you can calculate the equilibrium constant or the equilibrium condition. What's the difference when you have only single reaction? Actually, it's just the same. It's just the same. Everything is the same. So the thing that have changed is you just have to add the equation from this expression to the number of the chemical reaction that you have. As well, you have to add the equation of the equilibrium constant as to the number of chemical reactions that you have. For example, the J, symbol J here is referred to the number of chemical reactions. So if you have 3 chemical reactions, that means you have 3 equilibrium constants. And every equilibrium constant you can calculate from the same equation that you have done before. Yeah, so everything is the same. It just adds more step, more work, more task that you have to do when you have more reactions. That's it. Everything is the same. So for the chemical reaction equilibrium equation, right? So this one also have the number of the equation is equal to the number of reactions as well. So you will have the different equation based on different chemical reaction that we have in the system. And for the task that you have used, this equation is just the same. You just have to consider the system to change the fraction of the viscosity based on the phase of the species in the system. If it's gas phase, you can change the standard state viscosity into the standard state ratio. And you can change the viscosity in solution to the mole fraction and the viscosity coefficient equation. And if the reaction occurs at a very low temperature, then the viscosity coefficient in solution can change to the number 1 successfully doing it. So the equation here can simplify into this one. Everything is same. And if you change, if you retain, if you write the mole fraction of this species in terms of the reaction coordinate, then the equation can be solved if you know the pressure and the temperature. Okay, so let's just have a break here. After a break, we will go through the two exercise that you can see the example of the multi-reaction theory. So let's have a break until 2:40. 40 minutes.